concluded the previous section with an overview of runtime monitoring and how analyzers are relevant to us. In the last part of this series, we get down to the business of how analyzers are synthesized from sHML specifications. We discuss what it means for us to instrument the system with analyzers and demonstrate how this can be achieved using detector. Once again, we rely on our now familiar Erlang calculator server example to accomplish this. I'll cover the inline and outline forms of instrumentation here. Detector also supports offline instrumentation. I encourage you to visit our tutorial website for details on this type of instrumentation. Let's get to it then. By and large, runtime monitoring consists of two ingredients, the instrumentation and the analysis. Instrumentation lies at the heart of runtime monitoring. It refers to the extraction of information from executing software following one of two approaches. In the gray box approach, instrumentation is implemented by weaving the instructions that extract information directly into the program. Alternatively, instrumentation can leverage an existing tracing infrastructure to collect information externally. In this manner, the program we want to observe is treated as a black box. The instrumentation information we're after are program events, also known as trace events. Besides extracting these events, the instrumentation also reports these events to the analysis, which then processes this event stream to reach verdicts. The analysis role in our case consists of the analyzers that I'll show you how to synthesize from sHML formulae in just a moment. One thing to note here is that the instrumentation and analysis are separate entities. Think of the analysis layer as sitting on top of the instrumentation. Detector implements this separation of concerns as best as possible. Now, before we can instrument our calculator program, we need to first synthesize the analyzers. Let me show you how to do that. To disentangle the specification and analysis concepts, Detector uses the intermediate program event patterns such as fork, init, etc. These intermediate events are then internally translated to the ones that the Erlang virtual machine tracing infrastructure uses. We adopt this approach since it simplifies our implementation of analyzers. Detector parses sHML specifications, such as those we've seen previously, from sHML script files like this one here. These files are simply text files that contain one or more specifications that we would like Detector to synthesize analyzers from. For this demo, I will use the incorrect addition property we specified earlier. Let me comment the property description out, otherwise the file will not be parsed. To synthesize analyzers, use the HML eval module provided by Detector. HML eval supports a handful of configuration options, which I won't describe here, but that you can get details about from the tutorial website. So let's switch to the terminal, open the Erlang shell, and see how this is done. Remember to include the detector binaries in the shell code path using the -pa flag. Now that the shell has loaded, we type in HML eval compile. The compile function accepts two arguments, the path where the sHML file resides and a list of options. So for a file path, I will type props/example2.html. Note the HML extension. For the list of options, I will set the output directory to ebin by specifying this tuple tagged with outdir and ebin as a value. Next, I will use the flag earl so that Detector generates the analyzer source code instead of the compiled equivalent. Normally we don't do this, and I'm simply doing that here so that we can have a quick peek at the analyzer source code that Detector generates. Now, let's switch back to the editor and look at the analyzer source code. So the first thing that you should note is that the analyzer is one single higher-order function that returns other functions in turn. The functions returned encode the continuation formulae. Another thing that I should point out is that the init, send, and receive process patterns have been translated to events that Erlang uses for tracing. Let me point them out. The init event is translated to this tuple with the atom spawned. The send event is translated to this one here with the atom send, and the receive is translated to the one with atom receive. The entry point to analyzers is this hard-coded function mfa spec that accepts as an argument the function that we designated with the keyword with. Keep this function in mind, since we'll use it when we get down to the instrumentation, which I'll cover in the next two sections. In this specific case of our calculator server example, the targeted function was the function loop in the calc server bug module, which takes a single argument. The analyzers that detector generates from sHML specifications behave similar to state machines. Let me quickly walk you through it. So as I said, the keyword with that designates the function calc server bug loop is translated to this. The init event pattern we specified corresponds to this bit here. Next comes the maximal fixed point construct, which is translated to the named function x. This function name x will be used to recurse later on when we match the send pattern that contains the correct reply, consisting of the addition of a and b. Nested inside the function x is the function that corresponds to the first necessity that contains the receive process pattern. Finally, we have the two necessities that handle the incorrect and correct cases of addition. Once again, this function is nested inside the outer function that handles receive. It includes two function clauses. The first clause handles the case when the server reply is incorrect. Let me recall that for you. So it's this: box, server sends, OK, res. And the constraint is when the addition value instantiated in res is not equal to a plus b. This leads to the analyzer flagging an O verdict, which corresponds to a violation of the property ff. The second function clause handles the case when the addition is correctly executed by the server. So, box, server, sends, OK res, and the constraint now is res is equal to a plus b. The body of the latter function is just the invocation of the outer function named x, which enables us to emulate looping via recursion. Let me point out that each of the functions I discussed here has an extra catch-all clause. This clause matches any other event, hence the use of the don't care pattern here. Detector inserts these clauses automatically to cater for the case where the event reported to the analyzer is not the one expected. In such instances, the analyzer is unable to decide whether that event leads to a rejection verdict, that is, to a violation. If you recall from the concluding section of part 2, all that the analyzer is able to do here is just to say, I cannot say whether the program violates the property. Also note that since the functions are nested within each other, the variables in the outer functions bind the ones in the inner functions. This lexical scoping is what allows us to refer to the variables a and b of the receive pattern in the first necessity from the constraint of the second necessity. Now let me get back to the property. What I'll do is duplicate the specification. And modify the function under the with so as to target the calculator server that returns the correct result. To do this, I'll change the module name to calc server. I will use the second specification to give you a quick demo of the case where the analyzer finds no fault with our server implementation. Now let's synthesize the analyzer once more. This time, however, I will remove the error flag so that the compiled beam executable is generated. What I'll do is to use the V flag, and the V flag generates verbose analyzers that print out the events that they analyze. This will serve us later when we instrument our analyzer to see what's happening underneath. There, that compiled successfully. Of course, the resulting analyzer binary must be included in the code path of the program we are running. Note that we must also include the detector binaries. Next, we learn how to instrument our calculator program with this analyzer, using the inline approach. Inlining is the most efficient instrumentation method that Detector offers. While this instrumentation method assumes access to the program source code, it carries benefits such as low runtime overhead and immediate detections. In fact, there are other tools out there that adopt inlining as their instrumentation method of choice. One drawback of inlining is that it tends to be invasive and cannot be used in scenarios where the program code is not available. Detector instruments invocations to synthesize the analyzers via code injection by manipulating the program abstract syntax tree. The whole procedure is explained in a fair amount of detail in the companion paper, the link of which is provided in the video description below. I suggest you take a look if you're interested in the low-level details of how this is accomplished. Here, I'll demonstrate how you would want to use inlining to instrument a program with analyzers. For this, I will of course need the source code. Let's see how this is done. So from the Erlang shell, we first weave the program or programs that require instrumentation. To this end, Detector provides the Weaver module that offers two functions, one that weaves a single file and one that weaves an entire directory of files. We'll use the second version to weave both the buggy and correct implementations of our calculator server. The function weave accepts three arguments. First is the directory where the files to be weaved reside. Second is the main function of the analyzer we want weaved. And third is an option list. I'll go ahead and weave the directory where our examples are located. So I'll type weave and the relative path source demo. Then we use this syntax particular to Erlang to specify the module and function of our analyzer. We do this by typing fun example2 mfa spec/1. If you remember from the analyzer source code we've seen in the previous section, the function mfa spec acts as the entry point to the analyzer. The last argument is the list of options, and I'll specify that I want the weaved files placed in the ebin directory. These files will be automatically compiled and loaded for us in the Erlang shell. Okay, so now that everything is instrumented, let's try things out. We'll begin by first testing out the buggy version of the server. I'll go ahead and launch it by typing pid equals calc server bug start with an argument of 0. As soon as the server starts, the analyzer is immediately attached and promptly analyzes the first process event, which is init. Here we see that as the internal Erlang spawned trace event. Now let's try sending an addition request. As we did in part 1, we type pid exclamation mark and the message tuple consisting of the shell PID which we obtain using self. We also add the payload that consists of the tuple with add and the arguments. I'll once more use 10 and 97. There. And the analyzer says no, which corresponds to a violation of our sHML specification. What about a multiplication request? Let's try that. I'll stop the server and restart it once more. Note that the analyzer also processes the receive event containing the stop request, and its corresponding reply event. Keep that in mind, because I'll come back to it in just a bit. Now that the server has restarted, let's try multiplying two numbers. Immediately, we get to the verdict end. Can you tell why is this? Well, it happens because the receive event with a request of mal is not an event that the analyzer expects. In this case, the analyzer catch-all function clause is triggered, leaving us with end. That is to say, the analyzer does not know whether the program violates the property given this particular event. But I'll go further. What do you think happens when we try to perform an addition now? Let's try that. Oh, we get end as well, rather than no. Is this supposed to happen though? Let me explain. One important thing that we have to note is that our analyzers reach irrevocable verdicts. What does this mean? Irrevocable verdicts are verdicts that once given cannot be retracted and changed. If you think about it for a second, this makes sense. Why? Because in the case of safety properties, it wouldn't do for an analyzer to change its verdict, sometimes saying no and at other times I don't know. We want that if something goes wrong, then it's wrong, and the analyzer always sticks to that. In this case here, the analyzer reached the verdict end, and it will stick to that no matter what. Had the analyzer reached a rejection verdict no, then it would have stuck to that no also. Note that our sHML property can be refactored in a way that it accounts for and filters multiplication requests and focus on addition requests only. Perhaps you can try that yourself as an exercise. Let me give you a hint. You will need to add an extra recursive clause that handles multiplication. Now, let me stop this buggy server and try out the correct implementation, just to show you the case where the analyzer recurses. I'll start the correct server now. So once again, the analyzer is immediately attached to the calculator server process and analyzes the first event in it. Time to try out an addition request. We simply send the request by typing PID, ! and our usual payload. Now, what we see here is that the receive event is analyzed, as is the send event. Since this behavior is non-violating, the analyzer unfolds the recursion to start anew. Recall that this non-violating server behavior is captured by the constraint when res equals a plus b. Now that we've seen how to instrument our program using inlining and also tested that it works, I'll show you the second form of instrumentation. Outline instrumentation is the non-invasive counterpart to inlining. By this, I mean that the program is treated as a black box, so no changes are written to the program source code or executable. Outlining externalizes the extraction of and analysis of trace events. It leverages the native tracing infrastructure that the Erlang virtual machine provides. This infrastructure is used by a multitude of other programs targeting the Erlang ecosystem, such as the debugger. So, languages like Elixir and Clojure can benefit from this type of runtime monitoring. As I did for the case of inlining, I won't go into the nuts and bolts of outlining. Details of how outlining works can be found in the paper. If you're interested in an even more extensive account of how our outline algorithm works, feel free to check out our preprint, the link of which is in the video description below. Now let's get back to outlining. The first thing that I'll need to do before showing how outlining works is to recompile the calculator program. This we need to do since the current version of this program has been injected with the analyzer instructions that need to be removed. I'll terminate the Erlang shell and restart it. The included makefile erases all the program binaries, and we'll need to regenerate the analyzer from scratch. So, we'll launch the shell once more, and type HML eval, compile, and we specify the file props example2.html. Eben as the output directory, and the flag v for verbosity. There. I want to make it clear at this point that all we'll need for outline instrumentation to work is just the program binaries. All that remains now is to launch the program with the analyzers attached. Detector provides the monitor module to accomplish such a task. This module serves as the entry point to both outline and offline monitoring, which I won't cover here. We will need to invoke the startOnline function that accepts 3 arguments. The first argument is the tuple specifying the main function of the program we want instrumented. In this case, this is calc server bug, start, and its list of arguments, which consists of just the argument 0. The second argument of startOnline is the analyzer function we synthesized earlier, and the third, a list of options which I shall leave empty. StartOnline returns a triple as a result, tagged with OK and 2 PIDs. The PID that interests us is the one of the calculator server process. So what I'll do here is just pattern match against the return value of startOnline to keep hold of this PID. Note that as a function, I have specified start and not loop, because start is the one that launches the calculator server. OK, so once more, the analyzer is instantly attached and processes the first init event, which recall is translated to the Erlang spawned event internally. Now let's try to issue an addition request. And as you can see, a program violation is detected by our analyzer. By contrast to the inline case, with outlining, the analyzer can be terminated immediately to make things efficient. Why can we do this? Because once a verdict is flagged, the analyzer has outlived its purpose. Keep in mind that this is possible since verdicts are irrevocable, so the analyzer can terminate, safe in the knowledge that whatever it flagged will remain so. In fact, shutting down the server does not result in the analyzer printing additional output to the shell. There is one final thing I want to point out. If we start the calculator server by not going through the monitor startOnline function, it will work as usual. Let me show you. As you can see, when we issue an addition request, no analyzer activity occurs. This behavior is possible since the Erlang virtual machine tracing infrastructure can attach itself dynamically to processes and can be switched on or off. In fact, it is the reason why many Erlang profiling tools prefer this method of observing code that executes live on production systems. The correct implementation of our server works identically to the one we've seen in the previous section that discussed inline instrumentation. I'll skip that here, but you can test it yourselves as an exercise. In the tutorial website, you can also find out how to instrument the same example of the calculator server, but for an Elixir implementation. Try to attempt these tasks as an exercise, and let me know if you get stuck during this week. I will round off this section by underscoring the fact that we generated the analyzer once and used the resulting binary for both inline and outline instrumentation. We have seen Detector, a runtime verification tool for asynchronous component systems. In this tutorial, I covered the basics that should get you started with using the tool. We went over the specification logic used by Detector and how this can be employed to formalize useful safety properties. I went through the steps one should follow to synthesize analyzers from such specifications and how these can be instrumented with a program under scrutiny. Detector supports 3 instrumentation methods: inline, outline, and offline. I focused on the first 2 in this 3-part tutorial series. You can refer to the tutorial website to find out more about outline instrumentation and how this may be put to use. For this exposition, we looked at a simple calculator server program written in Erlang. Besides Erlang, Detector can be used with Elixir and other languages that target the Erlang ecosystem. The offline instrumentation component of Detector may be employed to monitor programs that run outside of the Erlang virtual machine. In the source code examples, you'll find an implementation of our calculator program in Python that uses TCP sockets. You can use this to test out offline instrumentation. We have used Detector in practice to monitor fragments of the Cowboy and Ranch protocols. These are industry standard applications used in the development of web apps. Detector has also been utilized to verify an implementation of the Raft consensus algorithm. The Detector project is fully open source and may be found on GitHub. Welcome comments, bug reports, and feature requests. Finally, thanks for taking this tutorial. I hope you found it both useful and enjoyable. Bye for now.